Hello, everybody. It is Mrs. Griswold here. Today we are on Unit 9B, Day 3, and we're going to spend the day reviewing for our test, which will be the next time we have class. So if you do have your notes, you can pull those out. The topic for today is review. It's 9B, Day 3, and the date will be different depending on what day you're watching this video. So we've got about 4 learning targets for this unit. We are not going to have different scores on the test for each learning target. You're just going to have one score. But these are the things we're testing on. So we learned how to calculate the probability using the fundamental counting principle. We learned how to simplify expressions in factorial notation. We learned how to calculate geometric probabilities. And we learned how to calculate permutations and combinations and distinguish between the two. So we're going to talk about each one of these things in this video. Okay, so the first thing is the fundamental counting principle. Okay, so the fundamental counting principle rule that we talked about in class, it says, suppose there are n1 ways to make a choice, n2 ways to make the second choice, and n3 ways to make the third choice, and so on, ... The number of possible outcomes equals the number of ways to make each choice multiplied with each other. Okay, one thing that might be a little bit tricky is how is this different from permutations and combinations? Well, the main reason why we would use the fundamental counting principle instead of a permutation or a combination is because we can use repetition in the fundamental counting principle, but we cannot if we're doing permutations and combinations. Okay, so if you come to a question and you're not sure, think about, am I allowed to repeat options? And if you are, then think you can use the fundamental counting principle. Okay, so first example of this, it says you must create a computer password consisting of 4 digits and 4 letters. Repeats are allowed. How many different passwords can you create? It's kind of like some of the things we did on the first day. So we've got 4 digits, okay, and then we've got 4 letters. Okay, remember there are 26 letters in the alphabet, and digits are 0 through 9. 0 is a digit, so that means we have 10 options for digits. Okay, how many different passwords can we create? Well, if it starts with digits, I have 10 options for the first one, 10 for the second, 10 for the third, and 10 for the fourth. Okay, well, what about letters? How many options do I have for letters? Well, I've got 26 options for the first, 26 for the second, 26 for the third, and 26 for the last one. Okay, then ultimately we're going to multiply all these together. It's going to be a big number. Oh wow, it's huge. You should have picked a smaller password. It is 4, 5, 6, 9, 7, 6, 1, 2, 3, 4. Let's see. What is that? Billion? Thousand, million, billion. 4 billion. Over 4.5 billion different types of passwords that can be created from 4 digits and 4 letters if you are allowed to repeat. That's a lot. All right, number 2. How many different passwords can you create if the first letter must be X? Okay, so remember we've got 4 digits. Same options for 4 digits, but this time the first letter must be X. So how many options do I have for that first letter? Well, I only have 1 option, but then I have 26 options for the next 3 as well. Okay, so this one's going to be just a little bit different. Still pretty large though, 1757. 6. Yep. So about 175 billion now. Reduces the amount because you have a little less options if that letter has to be X. Okay. Then lastly, how many different passwords can you create if the first digit cannot be 9? Well, that means I only have 1 option for the first digit. But remember, I can repeat, so then I still have 10 for the next 3. And then I can repeat for all of the letters. Okay, so let me see. And we get 4, 5, 6, 9, 7. Oh, it just has 1 less 0. Like, that's very... Wait. 6. Oh, I'm missing. I was like, that's too many decimal places gone. 4, 6, 9, 7, 6, 1, 2, 3. There we go. All right, so those are repetition. We would use the counting principle, not permutations or combinations. All right, next we talk about simplifying expressions using factorial notation. We did a lot of this stuff. You see in your homework there was all those simplifying and expanding and all those little steps. Okay, whenever we want to simplify expressions in factorial notation, you want to expand the larger number until you get to the smaller number for these. So I'm going to expand 97 factorial, which is 97 times 96 times 95 times 94 times 93 until I get to what's on the bottom, because now I can divide by 93 factorial. And 93 factorial on top will cancel with 93 factorial on the bottom. So we are very strategic in the way we expand. We're not just willy-nilly expanding. But when we multiply 97 times 96 times 95 times 94, we get 8, 3, 1, 5, 6, 1, 6, 0. Okay. So although that's not one we could do without a calculator, you should know how to expand and simplify that without just typing 97 factorial divided by 93 factorial. Okay, same thing with number 2. Okay, I want to simplify 6 factorial, or expand 6 factorial until I get to one of the numbers on the bottom. I want to pick the larger of the 2 numbers because that'll simplify it a little bit more for me. So I'll simplify 6 to 6 times 5 times 4 times 3 factorial. Pick the largest of the 2 to make it a little bit simpler. 3 factorial on the bottom will cancel with 3 factorial on the top. Now I can expand a little bit. Now I've got 6 times 5 times 4 over 2 times 1. Oh, I switched up my multiplication signs there. 6 times 5 is 30, times 4 is 120, divided by 2, 60. Okay, so that's how you would simplify by hand or expand it and show all those little steps besides just typing that in your calculator. Remember, work for tests are really important, especially things like this. Okay? Again, expand and simplify. Well, whenever we have an n, remember we're subtracting 1 each time. So to expand n factorial, it's going to be n times n minus 1 times n minus 3, and that is what I have on the bottom. So that is where I will stop and leave my factorial. Then I've got n minus 3 on the bottom, factorial. Those will cancel. And my final answer is n times n minus 1. You can leave it like that, or you can distribute in to get n squared minus n. Either one is okay. Okay, remember on the tests, we look through your work and we look through your questions. So if you type something in slightly different or around slightly different, we will catch that and you will get those points. You don't have to worry too much about how you're typing in for a test. Okay. Next one, n minus 1 factorial. That's going to be smaller than n plus 3 factorial. We want to always expand the largest of the 2 until I get to the smaller one. So everything that we've been doing before, or up to this point, and the other 3 that we did, they all had the larger one on top. Okay, this time the larger number is on the bottom, so I want to expand the bottom until I get to what I have on the top. So n plus 3, I subtract 1 each time, so the next one is n plus 2. Oh, I'm not going to have enough room. Then the next one is n plus 1. The next one is n. And now I get to n minus 1 factorial. So that's all on the bottom. Sorry, I ran out of room there. But I expand the larger until I get to what the smaller is, right? It's my strategic expansion. Not random, but strategic. Now I can cancel those out, and my answer, 1 is just left on the top. I still have n plus 3, n plus 2, n plus 1, and n. That's all left on the bottom. Okay, that would be a 4th degree n, so you don't have to multiply all of those out. Just leave it like that. Okay. All right, next one is I can calculate geometric probabilities. A dart is thrown as a target at the target, shown in the square dart. Assume the dart hits the board. What is the probability the dart lands in the small circle? Okay, so this one's pretty straightforward. Remember, we want our desired outcomes over our total outcomes. Okay, so the first thing we could do is we could find our total area. Okay, let me scroll down a little bit because we can't really see that number. Oh, it's a square, so it's 25. So 25 times 25, we get our total area is 625. Okay, now our desired area, right? We want to know what probability the dart lands in the small circle. Okay, so our desired area is this right here. Okay, remember, area of a circle is pi r squared. In this case, we've got 5 squared. That's going to give me 25 pi. Okay, so the probability is 25 pi over 625, right? Our desired area over our total area. Then we just type this into our calculator, and the probability that our dart will land in the small circle is 0.126. That's something like that. Okay. What about if I wanted, I'm going to add one because I know some of the ones on our homework and such have been a little bit more difficult. What if I said the blue area? What's the probability that the dart lands in that shaded area? Okay, this one is a little bit more involved, mostly just to find our desired area. So our total area is the same. It's still 625 for our total area because it has to land somewhere on the dartboard. That's what we're assuming. We're not assuming that you miss and hit the wall, right? So the desired area is that big circle, is just the blue. In order to get that, I take the area of the big circle, subtract the area of the little, right? And then I get that disc that goes around there. Okay, so the area of the big circle, well, the radius is 10, so it's going to be 100 pi. The area of the little circle, we just figured that out, is 25 pi. Okay, that is 75 pi. Okay, so our desired area of that little blue shaded region is going to be 75 pi. And now I divide to get that probability. Okay, so 75 pi divided by 625 is 0.377. All right, so obviously you know it's harder to get in the smaller circles or in the smaller area if you're at a dartboard. So it's less likely that you're going to land in the middle, a little bit more likely that you land in the blue disk, but we're not going to calculate missing the circle altogether. All right, next thing, I can calculate permutations and combinations. Actually, you know, I'll just show the whole, no, let's do that. Okay, so combination, NCR, that is the formula where N is the number of objects, right, and R is the spaces, I guess we would say. It's the same in both, right? So I want to arrange 10 objects in 4 spaces, or I want to choose 5 toppings from the 10 options. Okay? So combination formula is just slightly different from the permutation formula. It just got this extra R factorial term out there. Remember, with the combination, the order does not make a difference. So what that means, A, B, C, A, C, B, B, C, A, these are all the same, right? It's A, B, C. It's 3 letters. They're in a bag. It doesn't matter. It's the same. Like toppings on a pizza, right? If you get pepperonis and black olives, they put the pepperonis on first and then the black olives on second. It doesn't matter. You still have both of them on your pizza. Okay? Permutation, the order does make a difference. Example, if I had an arrangement and I wanted to make it look pretty, A, B, and C would look different on my shelf than B, C, A. So these are different. Okay? So that is the main difference of these 2 things when you're thinking about, you want to think, okay, does the order of these make a difference to my answer? Okay, then we talked a little bit about expanding and simplifying when we've got N in our formulas. So I want to talk about these to make sure we can talk about it together. So we plug it in the same way. It's just expanding and simplifying we can't do in our calculator. We have to know how to do in our head using what we know about factorials. So NC, N plus 2, let's see, let me plug everything in. N's going to go in the spot for N, so N factorial over, okay, N minus R. This whole thing is my R. N is my N, so I'm going to have N minus N plus 2. Don't forget those parentheses. That whole chunk is my R. Times R again, which is N plus 2 factorial. Oops, I forgot the factorial right there. There we go. Okay, now we want to simplify that as much as we possibly can. So this is the next thing that I see we can simplify. So N factorial on the top will stay the same. We simplify that, you have to distribute the negative into both pieces, and then I'll have N minus 2. Can you do a negative factorial? I don't know. No, you can't. Maybe that is why we don't do the N plus 2. I'm going to make a slight difference. Slight change. Let's change this to minus. Technical difficulties. means I'm going to change this to a minus. Okay. And that other one has to be changed to a minus 2 right there. There we go. That should work. So you can't take the factorial of a negative. So I should have thought of that before. So when we distribute, right, the simplifying process is the same, except when we distribute in here, we get n minus n, and then -1 times 2, which gives me n plus 2. All right, and then we still have n minus 2 factorial out there. Okay, n minus n will cancel. Now I've got n factorial over 2 factorial times n minus 2 factorial. Hey, there we go. This one's pretty involved. Okay, now we want to look at the factorials. We want to see which one's the biggest so that I can expand until I can get the factorial of the smaller one. N factorial is bigger than n minus 2 factorial, so I'm going to expand that. So that's going to be n times n minus 1 times n minus 2 factorial over 2 factorial times n minus 2 factorial. Now they cancel. And 2 factorial is 2 times 1, so it's just 2. So my final answer would be n times n minus 1 over 2. And you could distribute in n squared minus n over 2. That's okay too. Longer ones is a little bit messier, so you don't have to do that. Okay, so sorry, technical difficulties. Didn't realize that you can't take factorial of a negative. So we strategically picked where the minus, distributing the negative will turn into positive. Okay, now we want to do a very similar thing with just a different ends, but a different formula too, because now it's permutation, so I don't have that extra r factorial on the outside, right? This is my r, n is my n, so I write it in. I'm going to have n factorial over n minus r, which in this case is n minus 1 factorial. Now, keep simplifying. N factorial stays on the top. Distribute in the negative. So on the bottom, I have n minus n plus 1 factorial. N and n will cancel out. Leave me with n factorial. 1 factorial is just 1. So over 1 or just n factorial. That one was a little bit better. Okay. All right, let's get into, oh, nice. This video is getting long. That's okay. You don't have to watch the whole thing. Let's get into more about permutations and combinations. How do we find the difference? How do we tell the difference between the two? I think the more examples that you can see and that you can hear, you can be like, okay, yes, that's permutation. Yes, that's a combination, and so forth. Okay. So number 7 here, I'll put the shade so that we're not distracted by everything else. Says there are 25 people who work in an office together. 5 of these people are selected to go together to the same conference in Orlando, Florida. How many ways can they choose this team of 5 people to go? So in order to tell the difference between permutations and combinations, you have to know the difference between the order. Does the order make a difference or does it not make a difference? Okay. If I select 5 people to go with me to the trip, on the trip to Florida, it doesn't matter if I bring Kristen, Angie, and Sam, right? Or Sam, Kristen, and Angie. It's the same 3 people. So order does not matter, which means this one is going to be a combination. Okay? So we know it's going to be a combination. There are 25 people, and I want to choose 5 of them. So we write the formula is 25C5, and we get 53,130. Okay, I think the hardest part is determining whether it's permutation or combination. Once you know that, then you can write the formula and use your calculator. Okay, next one. There are 25 people who work in the office together. 5 of these people are selected to attend 5 different conferences. The first person in the conference will go to Hawaii. What is Hawaii? H-I? I don't know. The second person will go to New York. The third person will go to San Diego. We've got Atlanta and Nashville. Okay, there are 5 different conferences. Okay, so if I pick Angie goes to Hawaii, Sarah goes to New York, Kristen goes to San Diego, and I don't know, Chris goes to Atlanta, and another letter. John goes to Nashville, right? That is different than if John goes to Hawaii. And Angie goes to Nashville. So the order of how you pick those people and where they go matters because it will change where you go. So that means this is a permutation. Okay? Permutation means I got 25 people. I want to select 5 people, so it's going to be 20P5. That will give me 6 million different options. A little over that. Okay? John couldn't recall the serial number on his expensive bicycle. He remembered that there were 6 different digits, none used more than once, but he couldn't remember what digits were used. He decided to write down a list of all possible 6-digit numbers. How many different possibilities will he have to create? Okay. For a serial number, is the number 3678 and the number 3768, are those 2 different? Okay. Yes, those are different options, so this is a permutation. Okay. But the tricky thing is knowing how many we can choose from. We have 10. There are 6 spaces. Wait, you remember that there are 6 different digits. So there are 6 spaces. None of them were used more than once. He couldn't remember what digits were used. He decided to write down all of the possible 6-digit numbers. So we've got 1, 2, 3, 4, 5, 6 different spaces. We have 9 total, no, sorry, we have 10 digits we can choose from, right? 0 through 9. We know it's a permutation. So we have 10 total digits we can choose from, and we want to have 6 of them. You cannot repeat because none of them are used more than once. It's a permutation because the arrangement makes a difference. Okay. Last one. How many different 7-card hands can be chosen from a standard 52-card deck? Okay. If I have a hand of cards, does it matter if I have a king, a 1, an ace, a 3, and a queen in my hand? Is that different than having an ace, a 3, a king, and a queen in my hand? Are those 2 different? Well, think about it. If you were playing cards with your friends and you get dealt something, let's say you're playing Uno and you want to organize your cards in numerical order, right? You have those cards in your hand. Doesn't matter what order they're in, you have the same cards. So these are the same, which means it's a combination. We have 52 cards and we want to choose 7 of them. Those are all the possible options we can have. Okay? Again, let's determine a little bit more. Maybe I can make this slightly better. I know it's a lot of examples. Okay, but I think it's good we can determine the difference. Okay? So you must create a computer password consisting of 4 digits for letters, repeats, or a lot. How many different passwords can you create? All I want to do is say, is this a permutation, combination, or I guess I would say neither would be the counting principle, right? The key to this first one is it says repeats are allowed. That means it can't be a permutation or a combination at all because we can repeat. So this would be a counting outcomes one where we would do like 4 digits, you know, make the space, make all the spaces, 4 digits, 4 letters, just like when I did counting outcomes just a little bit ago. Okay, when you go to the pizza shop, you have 4 choices for the size of pizza: individual, small, medium, or large. You can also choose from either thin or original. 2 toppings are available for this shape, either round or rectangular. How many different ways can the pizza be ordered? Okay, so this one is interesting because I did say like toppings on a pizza for a combination, but that would be toppings on a pizza. Okay, for this one, we're talking about you can either have a size, right? How many different options do I have for the size? And then how many different options do I have for the crust, right? We multiply those options together. This is a counting principle. So it is neither permutation or a combination. Okay. Next one, Aaron has 6 autographed baseballs and room for 4 in his display case. How many arrangements? Arrangements is the key word for a permutation because the order makes a difference. I'm arranging in a permutation. How many ways can a group of 5 people be chosen from a class? Well, it doesn't matter who I pick. I'm going to have a group of 5 with me, so this is a combination. How many ways can 8 people line up for a picture? Well, if I'm going first versus me going 7th, that makes a difference to me, right? So that must be a permutation. The order makes a difference in that situation. Okay, Megan is buying 3 different bagels. The bakery offers 7 types of bagels. How many different combinations can she buy? So for this one, you see the word combination. Hold on, let me think about. She's buying 3 different bagels, and there are 7 types of bagels. Yes, you have 3 bagels. Let's say you get the cinnamon sugar. Oh, that's what I like. And you get the Asiago, and then you get the blueberry. You have those 3 bagels, right? They're in your bag, and it doesn't matter if you bought the blueberry or the cinnamon sugar one first or the Asiago one last. You have all 3 of those, so it's a combination. Okay? 4 people are running in a relay race. How many different ways can the 4 people be arranged? Right? If I come in first versus me coming in third, that's going to make a difference to me. So it's a permutation. What's the difference between permutations and combinations? Order makes a difference. You don't have to write the formulas. We just saw them on the previous page. Okay, so after all of that, I know that was a little bit long, but I feel like that's a pretty good comprehensive review of everything that we've done. Problems is talked through, looked at. Now that you've finished the video, what you're going to do is you're going to go work on the review on Delta Math. Make sure you are prepared and ready for our Unit 9 test. Well, I guess 9B test on Wednesday 3/31 or Thursday 4/1. I personally, Mrs. Griswold, only teach 2 and 6, so our test will be on Thursday. If you're wondering, it's 20 performance points, right? Each unit, we try to have 50 performance points. The 9A test was worth 30 points. This one's worth 20, just because it's a little bit less than all that other stuff. All right, go ahead and get working. Where's my mouse?